Cool. Oh, okay. So we've filtered everything out. Okay, so well, it's very good to be following Michael's talk because it will save me a lot of time. I don't have to re-explain everything. So I'm going to talk about one, well, actually my talk is broader, but part of my talk is going to be about a specific set of filters that Michael alluded to, so static or immutable filters. But I actually also want to start with Bloom filters because I've got my own approach to it, and you see, so I want to take a really practical, performance-oriented take to this. So, I wanted my talk to be accessible, like no doubt Michael. So I did not go into much theory. So that's the theoretical bound we've been talking about, right? So basically, if you want to add your error rate, the best you can do with your error rate is 1/2k, where k is the number of bits you have to invest per element. And so usually this was alluded to, so I don't need to repeat it too much, but typically it's not always true, but typically when you're dealing with filter, you've got a fixed initial capacity. So Michael talked a lot about that, and it can be difficult to update safely if you don't have access to the original set. And just like Michael said, you get about, if you're lucky, you can get a 1% false positive rate with 8 bits. So so basically, yeah. So a conventional Bloom filter is made of a bit set, and don't worry, I'm not going to repeat everything Michael said. And then you've got k-hash functions. Okay, and here's what's a little bit interesting. So how do you actually, so we understand that you've got to, in the worst case, you've got to check k bit positions, but typically the way it's implemented is not naively well, it can be implemented that way, but usually it's not, okay, I've got to check k bit position, so let me access k locations and then do the computation. Very often, if you write the code like in Java or in C, you're going to have a multiple step. You're going to first check for the first bit position, right? And if it's not 1, then there's no point. If the bit is not set, then there's no point continuing. So you're going to stop there, and if not, you're going to continue. So it's not true in general with a Bloom filter that you'll always access k bit position, and this matters a lot for performance. So so here I just copy pasted. It doesn't matter if you don't read. I think that's like C++ or something. It doesn't matter if you don't read it, but the important part here is that this is a typical implementation. But the important part here is that you've got a loop and with an exit condition, which is basically the actual code for the branchy approach I described. So Bloom filter. So yeah, maybe you want to change your filter, maybe. But Bloom filters are actually pretty good, and there's a reason why. There's a Lindy. The Lindy principle is that if something has been around for a long time, it's probably going to be around for a long time. So it's been around for 50 years. It's probably still going to be around in 50 years. So it's pretty good in many ways. One really cool thing about Bloom filters is it's really fast to construct it. And basically because the construction is that simple, right? You're just setting a lot of bits, and it can be for the processor, it can be like of course you've got cache misses and so forth, but it can be done very efficiently. Like setting a bit in a bit set is very, very fast. You can almost do one per cycle or something like that. You can, of course, if it's large, then you're limited by bandwidth and so forth. But if it's in cache, you can do it very, very, very fast. There's a flexibility. So there's the counterpart to what Michael was saying is that yeah, you sort of if you want to have very good memory usage, then you have to guess the right capacity. So if you tell me you've got you expect to have 1 million entries and you only have 10, then it's going to be wasteful. But it's not going to fail. The Bloom filter is not going to be dysfunctional. And it's even true if you predicted, like if you thought it's even true in reverse, importantly, if you thought you were going to have 1 million element and you've got 10 million, then the Bloom filter is not per se broken. It's just going to be rather useless because it's going to let everything pass through. But but it's still doing its work. Like it's still bug free. So that's what I mean by it can degrade smoothly, which is fairly nice. So it just doesn't like goes to hell. So basically that's the kind of curves you get, right? So you set the capacity, and then you know as the number of entries increases, because if you had a fixed capacity, just something like people really very often don't understand. I sort of manage or help keep in shape a popular Bloom filter implementation in Go, and lots of people come to me with bug reports. And very often it's the you know, they have to do with its scalability. Like for example, they say, well, okay, I might have like 1 million element, but I'm only going to put 10 in them. And then they're surprised, well, it's using a lot of memory. Well, of course it is, right? So you've got here, you can use a lot of memory per element, possibly if your filter is very, very empty. And then the counterpart to the memory usage is the false positive rate. So you've got, you know, a sweet spot, but if you exceed the sweet spot very, very quickly, you know, very quickly, and you can see here it goes up really quickly, you can get a false positive rate of, you know, well over 0.5 and up to 1 very, very quickly. And so you do get these kind of bug reports also when people will say, well, you know, because they don't realize that because the implementation typically does not tell you, like you don't get a warning, like, wait a minute, you've exceeded the capacity. You just get the false positive rate goes really bad, and then people think they have a bug, or rather you created a bug because, you know, okay. So the Bloom filters are pretty good there, but they do have some downsides, right? So the 44% above the theoretical minimum is not entirely great, right? But of course that depends on your specific application. You know, so AMD just came out with well, you're going to be able to buy processors with over 1 gigabyte of cache, you know. So in some cases, it depends on the size of the thing, but, you know, using a little bit more memory may not, you know, matter that much. But what to me, like, because I'm performance oriented, it matters is that sometimes at the query time, not at the constructor time, but at the query time, they can be slow. Because basically, if you have a large bit set, so if you get a large capacity, it's almost like the worst case scenario of having to check K for K large or for K sizable, K values in memory. It's like, at random locations. It's really basically if you want to have lots of cache misses, that's how you do it. So you have lots of choices for filters. The ones we've worked on recently were the binary fuse filters. I'm not going to present them in details, but basically they can be fairly competitive and they can use a lot less memory than Bloom for some false positive rates. So the ones we've worked on are in green and blue. So in some cases they can be competitive. They have the property of basically being static. So the way you're supposed to construct them is you tell me you have, not only you tell me you have 1 million keys, but you also give me the keys. So I have everything at once, and then I build them. But let me go back a minute here to Bloom filter. So how do they fare? So I'm going to look at these are actual measurements, right? So I'm going to look. So I can have 8. I just picked randomly, but you've got 8 filter. An 8 hash function version, which is not super practical, and one with 12 hash functions. And so in theory, you would think that you would always get 8 cache misses, so 8 accesses to memory with each query in this case, and 11 in this other case. But it's not actually what it works. So it depends very much whether the element is in the set or perceived to be in the set by the Bloom filter or not, right? So basically, if the element is in the set, so all of the bits are set, right? Then you have to check everything. That's why you almost get 8 and 11, so you get 7.5 and 10.5. So I've used here a fairly large, I think, a filter, Bloom filter containing 100 million elements. So it exceeds my my cache by a margin, but not entirely. Some of the queries I can be lucky and they're caged. That's why I don't get quite 8 and 11. But what happens when I query for something that is not in the set, then what happens, and this is with a filter that's configured for optimal optimal storage, then I get much better results. And the difference between the the 8 and the 11 Bloom filter cases is fairly tiny. And the reason is that basically, and you can think it through, basically when you're accessing the first bit, and roughly speaking, this is not quite exactly how the math is, but roughly speaking, if you're processing something that's not supposed to be into Bloom filter, you've got about a chance out of 50% chance of having the bit set. And so roughly speaking, you very quickly find you don't need to check 11 bits before you find one that is set at 0, right? So the performance, basically the Bloom filter can have, as far as cache misses are concerned, can have fairly good performance if things are not in the set. So if you're using a Bloom filter in a scenario where most things are not going to be in the set, then it's pretty good. So, and there are applications like that, right? So for example, maybe you're filtering for porn URLs. So maybe your university doesn't want you to enter playboy.com or something. And then in that case, well, you know, if you're on the same campus, then probably most URLs are not, you know, meant for porn site. I don't know. So in that case, you might be into this regime where it makes sense, right?
I have a question about those results. Like, I thought in the optimal configuration for a Bloom filter, basically that resulted in half of the bits being set. That was basically
Roughly, yes.
And so if you have the looping implementation where you stop as soon as you hit a 0, then the expected number of probes that you make is 2.
Yes.
So
Except that you have so that's the theory, except that your processor is going to run is going to be doing speculative execution. So okay, so that's a very, very good comment. So if you do the math, right, you get 1/2, 1/2, 1/2. Yeah, it's not exactly 50%. It's very close, but you know, but okay, but it's roughly half. And in theory, you would get about an expected number of hits of 2. But it doesn't, like our processors are very, very smart, and they try to run ahead of you. And so it's not true. They'll try to predict where it's going, and they're going to preload everything and undo it. So
that 3.8 and 3.5, that's really a 4. I mean, it's really like speculative execution means that you're basically.
Well, it's what I actually measure, and my source code is available. Actually, I can point at that.
That's cool.
But basically, this is actually, but yeah, it would probably go to 4 eventually, but it will depend probably on your processor, right? So that's why I specify here. It's a recent Intel processor, but. Is there? Okay, right. So this was an excellent question. Okay, that's why I stress it was measurement, right? So now we can look at another metric that we often use for, you know, in software performance is the number of mispredicted branches, right? So the way processors work these days is that they have a huge execution queue that can, you know, the window can be quite large. It can be like hundreds of instructions, and they don't wait for the results of the comparisons of the HIF branches to be resolved before they do the computation. So they predict, and there were, you know, like some famous security bugs related to that, you may know. So they will try to predict ahead of time. And what do you try to avoid are mispredicted branches, because mispredicted branches basically means that the processor predicted we would go this way, but it does not pan out. And so then it has to roll back, cancel the computation, and restart. And that's at least 15 cycles of penalty. And it's not going to get a lot better over time. Rather, what the vendors like AMD and so forth do is they try to improve the branch prediction. It's really hard for them to make the cost less. So what we see here is that it should be obvious is that if all of the bits are set to 1, then you check all of them. That's really good. And then you don't mispredict anything because it's perfectly easy to predict. Whereas the opposite is true. Basically, if the value is not in the set, you're basically almost guaranteed to get a mispredicted branch. Now, why would I care about mispredicted branches and not about cage misses? Well, it depends on the size of the thing, right? So if the filter is tiny or it fits in cage, right? Your memory accesses might be quite cheap, and comparatively, the mispredicted branches start to, you know, being costing you more. So you have to balance these two. So this is for bloom filters, right? So here I just went with and I find that very interesting. I went with actual performance measures. So in this case, I just measured the number of cycles that it costs me per access, essentially. And if I always do accesses that are not into filter, right? Basically, you see here, and this is for a large filter. I see basically that the cost. What is interesting is that it's not very much dependent on the number of hash functions, and this makes sense if you recall my previous discussion. Whereas, of course, it does increase substantially when it's always intersect, right? So they're basically different patterns of performance depending on where you want to go. Very quickly, this is my short talk. So I wanted to allude to another extreme that I find very interesting: the block bloom filter, right? So the block bloom filter is something that's at least a decade old at this point, and probably more. And basically, the idea is that it's like a bloom filter, but what you do is, for a given entry, you only look at the bits that are within a small region, right? So it's exactly the same thing, but you take your entry and you're only allowed to hash it locally. What's really interesting about block bloom filter is that there is a penalty with respect to storage. It's not as concise as bloom filter, but it's actually not that bad. Like the penalty, it's not going to use like 3 times as much memory as the bloom filter. Like it's not that bad. Of course, it depends on the size of the window. And you can use SIMD instructions to really reduce the instruction count, which can matter if you're in some cases. So it's really fast. It's really hard to beat because basically you have few instructions, you have few cache misses, everything is nice. In the case we're using 64 bytes windows, you're basically like 56% above the theoretical minimum. It's just really not that terrible as a penalty.
Right, the theoretical minimum for a bloom filter or for a filter?
For filter in general, which is,
Whereas a bloom filter is like 1.44.
well, yeah, it's 1.44, so this would be 1.56.
You only lost 0.12 or something.
Yeah, you don't lose a lot. So this is actually pretty good, right?
So is this empirical number because
Yeah. This is empirical. This is empirical. I've got the code. If so the implementation, like don't I'm not going to explain it, but the implementation might be really concise with very few instructions, right? But this can be really nice.
Actually, how big would you want the blocks to be? The block bloom filter, what would you?
Well, I mean, here, well, in this case, this would be like in this case, this would be like 32. In this implementation would be 32 bytes. The thing is that as you grow it, it does not. Like you need to grow it a lot before you've got diminishing return, right? So if you look at, if you only have like obviously I don't have the numbers right now, but if you have 2 bytes, then it's going to be terrible, right? Now if you got 8 bytes, it's going to get bad, but not so bad. The slope is very, so it doesn't, in my view, it makes no practical sense to go above 64 bytes, I think, in practical sense, because basically it just matches the cache line. and CPU, which is a very nice, most CPUs have a cache lines of 64 bytes. So for those who don't know, the idea is that when you access your RAM, right, you don't read just 1 byte. The minimum you can read is a cache line, or at least pool, and that thing is 64 bytes. So a random access, if you're going to do a random access, there's not much like accessing just 1 byte. It might be cheaper than accessing 64 bytes, but not by much if it's a memory access.
Also, is this 56 number true across values of epsilon or just for some specific epsilon?
Right? No. That's specific to an epsilon. Like you don't you don't get. So basically, to answer the question here, so basically you've got some constraint here, right? Because basically you're setting the way I would design it is that you pick your window size, and then you figure out the best epsilon, the best storage, and so forth, and that's what you use. Now, if you very like you don't have the flexibility of Bloom filters where you can just use 20 like this code is not flexible. It's not going to let you change the number of
For what value epsilon?
It's going to be of the order, like I probably have the answer later, but it's probably going to be of the order of usually you aim for something that's close to 1%, into 1% range, basically. And there's an interesting reason for that, basically, because if you go, and it's related to Michael's talk, is that it depends on the applications, but basically some people think, well, I'm going to have this filter, and this filter is going to have a 0.00001. Why not? A percentage of false positives. Well, yeah, but at some point, it's no longer practical, because you might as well, just throw it away and build the whole thing, because you do have an overhead, right? So you do have to check your filter first, and then the real thing, or sometimes you do at least. And so having like a really huge filter does not make much sense. Okay. So really quickly, I wanted to talk about binary fuse filters. So I'm not going to present them in depth. I just want to scan it really quickly and just keep on presenting some experimental results. I'll try to go quickly. So basically, it's based on theoretical work. It's a fingerprint design, as Michael explained. It's immutable. That's fast construction, and it's fairly dense, right? We have 2 versions, 3Ys and 4Ys, that we find practical. You could go on, but basically, this is the number of filter to hash functions. So this is 3 axes, this is 4 axes, right? And basically you can see here the overhead as opposed to like 44%. So it's much better than a Bloom filter in this way. And I'll conclude my talk later about another way why it might be better. So it's fairly simple. The queries are fairly silly. What you do is you access 3 locations, you XOR the result, and actually my slide is wrong, because you should not have the equal 1 here. So you just XOR the 3 fingerprints that you find at 3 locations, and you check that it matches your target computed fingerprint. So it's basically, as far as software goes, it's like 3 or 4 axes. You XOR the result and you compare. All right. So regarding a prior question, what's the flexibility? Where, to be practical, right? You don't have to do that. But if you're a practical engineer, you're probably going to work with whole word. So 8 bits, 16 bits, 32 bits would be a bit much, but you know, like it's possible to implement it with a variable number of bits, but it gets, you know, more less efficient. And so the implementation, you don't need to read C, but looks like that. Basically, you access an array, you access an array, you access an array, and then you XOR and you compare with the computed value. Okay. So what's basically the performance here? Well, it's basically as far as cache misses are concerned, it's 2.8, and here it should be a 4. So for the 4-wise case, it should be, so it gets close to 4, but not quite, because processor is able to avoid some cache misses. And the misprediction, well, there are none, because it's basically not a branchy computation. There's no branch, there's no branching at all. So the misprediction are done at 0. Okay, so how does it compare with the Bloom filter? Well, you can see that you're using much less storage, close to optimal, and that it's generally, you know, at least a little bit faster than the Bloom filter, but especially so when you're hitting something that is in the filter. Because if something is not in the filter, then the Bloom filter is already like fairly efficient, right? Because and this makes sense if you think back at me counting the number of cache misses, right? They were similar. The Bloom filter has roughly as much cache misses as the other guys, but it has some overhead because it's doing speculation. Sometimes it gets it wrong and so forth. So it's a little bit less efficient, even though it may than something like binary fuse filter, even though the number of cache misses is about the same. But the difference is not huge. Here, these are times, right? This is the number of CPU cycles, and at the end here, it's the number of bits per entry.
So
yes.
If you wanted to really drive the bits down the entry, could you just increase, instead of doing 4-wise, could you do like if you do?
Yeah, you can go 5-wise and so forth, but then of course the cost increases. There's another thing I don't discuss here is that there's a scaling factor. For 5-wise would be we use less memory conditionally on the fact that you need to have a filter that's a certain size. So but because there's some, if the filter is too small, right, you don't get to this, there's a little bit of penalty. So basically, like if you went with like 12-wise filter, right, in theory, you would get like very, very close to the optimal. But in practice, it would only work for relatively for gigantic filters, so it becomes non-practical. That's why, like, you could go at 5, it could be practical, but I think anything beyond 5 would become, you know, silly.
Because I remember in Dietz Filbinger and Phase paper, they had some result where with log n times 3, your space wastage became like order log n bits or something like absurd, like something super small. And so I was wondering if you have, so I had the impression from that paper that kind of as you increase your time, your space usage, even the constants drops dramatically.
Well, I mean, the bound, I'm not sure I'm understanding the question, but the bound that Michael gave is hard bound. Like you can't, like if you're spending 8 bits, you can only, your false positive rate cannot be worse than, in general, than 1/2.
I'll follow up later.
I was gonna say, I think the idea is like, is the the additional term, is it an additive or is it like, see this multiplicative term with Bloom filter, you can also have an additive term in terms of the number of elements.
Oh, the number additive. Oh,
Or you can have a smaller than additive term in the number of elements, which is,
Oh.
I think, what you're getting here, but I think that's kind of.
okay. That's a different. Okay, that's a different. Okay. Okay. But yeah, but basically, I think that's pretty much practical. And 2i's is not practical because it's too inefficient. So what it looks like, so basically, here, these are examples where here we have the storage and percentage above the minimum, and we're using different implementations. You see here to block filters that has a not a great false probability, but relatively speaking, it's not using that much storage. We have our guys here, the binary filters, and you have the query time to fairly efficient. And so is the vector quotient is also fairly efficient as far as query time is concerned, and you've got other implementations that are somewhat less efficient, like the Bloom filter is one of the slowest. The conventional Bloom filter is one of the slowest, and it's also among those that use the most memory. So our binary fuse, I'm not going to describe that because it would be too technical, but very quickly, they can be constructed very quickly. And one of the reasons is basically that we have a trick where we do some kind of sorting, which makes it that we basically we don't, if you construct it naively, it will be fairly slow, but we have a trick, and I refer to paper, but basically we sort it so that basically we get a very fast construction time. It's not quite as good as the Bloom filter, but it's basically top of the line as far as construction goes. And that's important when construction needs to be fast because they're static, so you cannot update them. So the size matter. So I use it to that in some cases. So here I'm using, these are real numbers, but it's based on my laptop. And I'm using a small filter. And what's really interesting here is that you're basically getting a scenario where black Bloom filter, I'm using neon instruction, and here it should be a 3. And our binary fuse filters have basically the same performance, and the Bloom filter is considerably slower, right? And it's slower both in the case where it's all in and in the case where it's all out, right? And that has to do with, despite all the optimization, it still generates a lot of instruction, right? And even and so there are different ways possible you might be able to optimize the Bloom filter more, but for a hot small filter, basically all these approaches are fairly similar performance wise. Of course, the binary fuse filter that I'm pitching do better as far as storage goes.
So like even for the compared to Bloom filter, block Bloom is taking slightly higher space, and the error rate is almost 3x, right?
Yeah, so the block Bloom filter in this case is using more memory than any other guys.
Yeah, but the error rate is also 3x almost than the Bloom filter. Oh, sorry, it's a 2x, yeah.
Yes.
1.5x.
Yes, so it's definitely using, so it's not fair to compare it directly because it's got a worse FFP, but but basically if you look at the real number, it's not terrible. Like you're not going to get fired if you're at Google and you implement a black Bloom filter, right? It's not a terrible idea, right?
That's because at Google, no one's actually paying attention to what you're doing.
Could be, I never worked there. Okay, so, okay, so here it gets very, very different when you increase the size of the filter. If you increase the size of the filter, that's where the block bloom filter gets really, really competitive, because then it's got this magic where it basically just hit one cage line, and so it gets highly competitive. It gets much faster than the other guys, and that's why if you don't mind spending the memory, it can be like fairly unbeatable. Of course, stress that as it's great that Michael was there before, because then he explained that, okay, but there are other operations you may want to support, and so I'm not going to go over the limitations of these guys, but basically these two have to support more or less the same operations, and these are static. It should be a 3, by the way, and these two are static. So there is a trade-off. Okay, and I'll conclude with that. So one thing I wanted to do just for fun is what happens if you take a filter and you try to compress it, and basically I just take the array, and there are papers that explain how to do this better, but I just wanted to be like a Google engineer, but not in a bad way. And I just apply, I start a compression routine that's state of the art, ZSTD, and just compress it, and with the default setting, and see what happens, right? And what you see, in my case, at least, and I've got all my code, the blue filter is not very compressible. And this makes sense because, at least with a generic technique like that, it makes sense because basically each bit has a 50% probability of being 0, 1. That's pretty hard to compress in general. There are ways to do it, but it's fairly hard to do, right? So basically you get no compression. But these guys, okay, and this would be true of pretty much all of the, or not all, but many of the fingerprint-based schemes, they're fairly compressible. And why that is because all the extract capacity you have can be filled with zeros, basically, right? So the way I didn't go through it because I wanted to respect the time, but basically you've got this array of fingerprint, and in the case of binary fused filters, what you do is that you don't use all of the space. Some of it is unused and it remains at 0. And this means that this is actually compressible. Now you could use a fancier technique, but a generic compression technique is always good enough to actually come and capture some of these benefits. And this is likely something you would do in practice if you were sending the filters over to network, right? Because very often over to network, it's worth spending extra time building it up. Okay, so I probably went over my allocated time. I just wanted to point that we've got lots of pointers to all of our implementation. The last one is something that's we've stolen bits and pieces from all over the place, and we put them together. And basically, we've got this huge benchmark where you can try like a large number of filters and compare them experimentally. And you get like all of the fun stuff, like the performance counters if your system is supported and so forth. And so you can do that. And if you want to bug me, you can come and use the Bloom filters and Go. I get lots of issues and weird bug reports that are not about bugs and so forth. And yep.
Thank you so much. So I guess we have 10 minutes before the break. So we're running behind 2 talks now.
We could have 2 things.
So yeah.
Let's do one more talk.
Let's do one more talk and then we can do the break. And
Hmm?
Stop.
Yes, I will.
For video as well? Yeah, I will just click this again.